In the previous videos, we analyzed the different types of breakdowns and their economic impact. We now move on to the most important part from an operational and financial perspective: how to anticipate failures to improve profitability. To achieve this, there are four fundamental pillars that every O&M strategy should consider: N+1 redundancy, an advanced SCADA system, predictive maintenance, and good component selection. N+1 redundancy, for example, allows operations to continue even if a component fails, thanks to parallel configurations and automatic switching. This guarantees availability of up to 99.9%, which means fewer downtimes and increased production. Advanced SCADA, meanwhile, allows for 24-hour monitoring and early alarm generation, reducing fault detection time by 45% and improving the technical team's response capacity. If we combine this with predictive maintenance, the use of artificial intelligence algorithms that analyze patterns and detect failures before they occur, we can reduce unplanned incidents by 60%. But detecting them isn't enough. What we work with also matters. Selecting components with Tier 1 certifications and a good field history increases the mean time between failures by 25%, which in turn reduces the maintenance burden and the risk of critical downtime. Added to this are emerging technologies such as AI diagnostics, which anticipate failures up to 30 days in advance and adjust parameters in real time, or energy optimizers, which help mitigate shadowing effects and enable string-level monitoring. From a financial perspective, all of these strategies have a clear return on investment. For example, N+1 redundancy implies an 8% increase in CAPEX, but saves up to 65% in losses due to production downtime. Advanced SCADA, with an estimated cost of around €25,000 per 100 megawatts, can save up to €150,000 per year in O&M costs. And predictive maintenance, with an investment of around €60,000, can reduce critical failures by 60%. The roadmap for implementing these solutions can be approached in different phases. First, a systems audit, then the deployment of advanced SCADA, the configuration of critical redundancy, and finally, the implementation of predictive maintenance. If all of this is implemented correctly, the strategic objectives are achievable: achieving 98.5% availability, reducing mean time to repair by 50%, reducing O&M costs by 30%, and improving overall return on investment by 20%. In short, the tools already exist, the returns are proven, and what makes the difference is execution. Photovoltaic plants that integrate these strategies will be more efficient, more profitable, and better prepared for the challenges of the energy future. So far, we've discussed how to prevent and reduce failures in today's inverters, but it's essential that we also look ahead with a strategic perspective. Technological evolution in this field is not only rapid, but profoundly transformative, especially in the context of utility-scale plants, where every additional percentage point of efficiency represents thousands of euros in savings or operating profit. Now, we need to open a window to the near future and explore four emerging technologies that are already beginning to change the game: microinverters, power optimizers, string-level monitoring systems, and artificial intelligence-based predictive diagnostics. Microinverters are a distributed solution that breaks with the traditional centralized inverter model. By assigning an individual MPPT to each module, much more precise optimization of energy production is achieved. This translates into greater overall system efficiency, even in situations of partial shading or in installations with uneven inclinations or orientations. Furthermore, they have a very valuable feature: redundancy. If one of them fails, the rest of the system can continue operating unaffected, reducing the risk of a complete shutdown. Although their CAPEX is still high compared to other solutions, field data shows they can increase average production by around 15%. This technology, although more common in residential or commercial environments, is beginning to emerge as an alternative in utility-scale projects with modular designs. Power optimizers, on the other hand, operate within the DC system, where they improve safety, enable rapid shutdown in emergencies, and, above all, correct imbalances between modules that cause mismatch losses. In plants where strings are not perfectly balanced, their application can reduce these losses by up to 95%, justifying their analysis as a viable solution in certain cases. However, their implementation must be carefully evaluated, especially if there are budget constraints or if the design is already homogeneous. A's for string monitoring. This is probably the most immediately and widely adopted technology. Its low cost and high impact make it ideal for both new plants and existing facilities looking to improve their diagnostic capabilities. By providing precise visibility into the performance of each string, it allows faults to be quickly identified, the source of the problem pinpointed, and the average diagnostic time to be significantly reduced by up to 70%. This not only optimizes operation and maintenance tasks, but also contributes to reducing downtime and increasing the overall availability of the photovoltaic plant. Artificial intelligence diagnostics represents a further evolution in the approach to predictive maintenance. Thanks to the analysis of historical patterns and machine learning, this type of system can anticipate failures up to 30 days in advance. This predictive capability translates into a clear competitive advantage. We can intervene before a serious breakdown occurs, better plan resources, and avoid unscheduled downtimes. Furthermore, many of these systems are already being integrated into advanced SCADA environments and are showing high ROIs in the range of 20 to 30%, especially in plants that already have a solid data infrastructure. Looking at the medium-term technological projection, we see a fairly clear roadmap. Between 2024 and 2025, string monitoring is expected to be widely implemented as a design standard. Between 2025 and 2026, predictive artificial intelligence will become an essential part of energy management systems. Starting in 2026, we will see microinverters begin to scale in larger projects, and by 2027, we could be talking about fully autonomous systems capable of adjusting and diagnosing themselves without direct human intervention. From a financial and strategic perspective, the cost-benefit matrix provides some very useful conclusions. AI and monitoring technologies offer a particularly favorable investment-return ratio. With moderate investments, significant improvements in performance and availability are achieved. However, both microinverters and optimizers require more detailed analysis, as their effectiveness and profitability depend heavily on system design and site-specific conditions. Therefore, our recommendation is clear. Prioritize string monitoring as an immediate, high-impact action. Introduce predictive AI gradually by leveraging available operating data, and consider power optimizers in situations with a high risk of mismatch. Microinverters, although more expensive today, should be kept on the radar as a future solution with great potential. In short, technology is no longer just about fixing things when something fails. Today, it predicts, optimizes, and learns continuously. And the real competitive advantage lies in anticipating them. Adopting these innovations early isn't just a technical decision. It's a strategy for reducing costs, maximizing production, and positioning yourself ahead in a market where every improvement counts. We're in the final stretch of analyzing inverter failures, and we're doing so by connecting all the points discussed in the previous videos. We've reviewed the main failures in photovoltaic inverters, analyzed their causes, evaluated their technical impact, and, most importantly, quantified their direct economic impact. Now it's time to take a step further. Transform all this information into a set of practical, organized, scalable actions, aligned with both the operational and financial objectives of any utility-scale plant. We know that inverters not only account for 43% of failures recorded in photovoltaic systems, but also cause 36% of total energy production losses. These percentages aren't just numbers. They represent thousands of euros in undelivered energy and corrective costs that could have been avoided. Translated into concrete economic terms, we're talking up to 38 euros per kilowatt peak per year, a figure that directly impacts annual OPEX and, accumulated over time, can jeopardize the project's expected profitability. Furthermore, with a mean time between failures, MTBF, of 1.165 years, we can assume that most inverters will suffer one or more failures throughout their useful life if preventive action is not taken. Reducing this risk requires clear decisions. Establishing N+1 redundancy in the most critical inverters is a key first step. This configuration allows production to be maintained even if one of the units fails, avoiding total shutdowns. But that's not enough. It's equally important to ensure continuous and systematic maintenance of the cooling systems, as most thermal failures originate there. It is also essential to implement an active monitoring system for IGBTs and capacitors, components that often fail without warning and whose replacement involves not only cost in parts, but also downtime. And of course, it is essential to establish a rigorous, validated, and secure protocol for firmware updates, which minimizes human error, incompatibilities, or vulnerabilities that could compromise inverter performance or communication with the SCADA dot. These strategies have a cost, yes, but the payback is often faster than many budgets anticipate. Tools such as Advanced SCADA, which allow real-time visualization and control, or predictive maintenance systems based on artificial intelligence, not only prevent failures, but also improve overall operational efficiency. Autonomous diagnostics, capable of identifying patterns before they translate into actual failures, allow for just-in-time intervention. To translate all of this into a clear roadmap, we propose a progressive plan for 2025. In the first quarter, we will conduct a full audit of the plant's most critical systems: inverters, communications, cooling, and protections. In the second quarter, we will implement advanced SCADA and redundant configurations where they do not yet exist. In the third quarter, we will develop customized predictive models for the plant in question, tailored to its climatic conditions and operating profile. And in the last quarter of the year, we will begin the controlled integration of emerging technologies that allow for the automation of diagnostics and optimization of operating parameters without human intervention. At a strategic level, the focus must be clear. Investing in technical reliability from the outset is often more cost-effective than seeking initial CAPEX savings. Investing in Tier 1 inverters, with a proven track record in the field and high compatibility with state-of-the-art SCADA, offers greater operational peace of mind. Furthermore, there are low-cost, high-impact technologies, such as string monitoring, that should be implemented from the outset. Beyond equipment, it is essential that the plant's technical team acquire internal skills to interpret data, anticipate failures, and use artificial intelligence tools with technical judgment. The next steps are relatively simple, but require decisiveness. First, technically assess the current status of all inverters in operation. Then, compare them with similar plants that have already adopted these practices to identify opportunities for improvement. Next, design a mitigation plan tailored to the plant's actual context, and finally begin the progressive implementation of solutions, validating each step to ensure tangible results from the outset. If we follow this strategy, it is realistic to achieve an operational availability of 98.5% and reduce maintenance-related costs by half. And with this, we arrive at the final message of this video series. The goal is not simply to repair faster, but to fail less. That is true efficiency. To achieve this, we need to change our approach, moving away from reactive approaches and toward a preventative model, supported by data, digital intelligence, and well-founded decisions, both from an engineering and financial perspective. I hope you enjoyed this video series and that the comments reflected in these videos will help you in your daily life. Send me a private message on LinkedIn, and I'd be happy to receive your constructive feedback for future videos. Thank you very much, and best regards.